classes we have studied about the characteristic curve of different configurations of transistors, and we have seen that the active region, the saturation region and the cutoff region, these are the three operating regions of the transistor, but under normal operation as an amplifier, the transistor is to be biased in the active region. The saturation and cutoff regions are only used for exclusive applications like switching and cutoff. So, now the transistor, when it is used as an amplifier, the first and foremost thing to remember is that it has to be biased in the active region. So, if it is properly biased in the active region, when we give a small AC signal at the input of the transistor, then it will be able to amplify it to a large signal, and this amplification again has to be proper because the shape of the input voltage signal has to be maintained correctly without any distortion. So, the faithful amplification of a weak signal is done by a transistor amplifier if the transistor is biased properly in the active region. So, we will be discussing about biasing the transistor today. Biasing means the proper selection of the operating point or maintenance of proper level of DC voltage and currents in the transistor. So, under DC circuit, if we consider a transistor, then we have a figure like this. Here we are using an NPN transistor which is common emitter, and we will be throughout our discussion using common emitter transistor because of the fact that it has high current amplification factor beta, which will be used for amplification of an input signal. This beta value is high. So, common emitter transistor is normally used for amplification purpose. So, using a common emitter transistor in NPN configuration, we have this input circuit between base and emitter. Emitter is grounded by VBB, biasing is done, forward biasing in the input circuit, and the collector base junction is reverse biased by the application of the source VCC. So, in this circuit, resistance RB and RC are connected in the base as well as the collector circuit, and this is practically what is done in a transistor biasing. And if we now consider application of an AC signal at the input, suppose we have an AC signal Vi along with the biasing voltage VBB, this is being applied at the input, and our purpose is to amplify this weak signal faithfully. That means, we want the magnitude peak to peak of the input voltage to be magnified without any distortion in the shape of the input signal. If it is a sinusoidal, we want perfectly sinusoidal output at the collector, and it should not be distorted in any portion throughout the cycle, but we want the magnitude to be amplified, peak to peak voltage should be magnified. That is the basic of amplification. So, here when we have an AC signal along with the DC voltage VBB, the currents which are earlier flowing in the DC circuit were the DC currents IB, IC and IE. Now, because of the application of the AC signal, we will have AC currents also. So, now considering the base, we will have an AC current small I small b denoting the AC quantity along with the DC value IB. Similarly, the collector current will be capital IC plus small ic. So, the instantaneous current in the collector will be capital IC plus small ic, capital IC being the DC component of the instantaneous current and small ic being the AC component. Similarly, in the emitter we have capital IE plus small IE, and if we consider the voltages, then the base to emitter voltage will be capital VBE plus small VBE, and the collector to emitter voltage is capital VCE plus small VCE. Here we are having the symbolic representation of the instantaneous current and voltage by small I capital C or small I capital B or small I capital E, denoting that this is the instantaneous current. Similarly, small v CE, when we write CE being capital, V being small, we mean that it is instantaneous voltage which is a combination of DC as well as AC. Now, this is the symbolic representation for the instantaneous current IB, IE and IC, where the capital part or capital notation is used for the DC and small notation is for AC. So, now what we see here, when we apply a small signal, apart from the DC biasing voltages, there will be current flowing in the circuit which will be having two components. So, one is the DC component and on it will be superimposed the AC component. And here if we notice, if we consider a small I small c, this is nothing but beta AC small I small b, where this beta AC is the AC beta value, and this is magnitude wise not very different from the DC beta value. AC beta value and DC beta value are almost magnitude wise same, only a little difference is there. And similarly, the small alpha for AC, that is alpha AC and alpha DC, these are also magnitude wise not very different. So, for all practical purposes we can assume that beta and alpha having same DC and as well as AC values. So, now again if we look into the AC and DC components and the overall instantaneous current and voltages, then we see here in these plots, when you have only DC conditions prevailing, suppose we are not giving the signal as such till now, only the biasing voltages are there, then due to the DC biasing, that is the input circuit is forward biased and the output circuit is reverse biased. So, for that condition we are having the DC condition prevailing and the current and voltages for the DC condition is, this is the point of operation, Q point it is called, and the DC base to emitter voltage if we consider, it is VBE, this point is having this base to emitter voltage VBE, capital V capital BE, that is the DC voltage, and the current flowing in the base which is capital I capital B, the DC current is IB. So, for that particular voltage, this is the current IB. So, the Q point in the input characteristic defines the DC voltage between base and emitter and the base current IB. Now, we are applying a small signal, say, due to the small signal at the input, if we look back into the circuit, due to this small signal, another current flows which is purely AC. So, that current is denoted by small I small b for the base, and corresponding current in a collector which is purely AC, that will be small I small c, which is equal to beta times, beta means the AC beta into small I small b. So, this base emitter, base region if we see and we concentrate on the input characteristic, that is the characteristic between the base current and the base to emitter voltage, we have a change in the VBE due to the application of the signal. So, if we consider the DC VBE, then when the signal is in the positive half cycle, that small signal is in the positive half cycle, we have increment of this base to emitter voltage. Initially this is the DC VBE, so it will be increasing due to the application of the small VBE, it will be rising in the positive half cycle and it will be reducing in the negative half cycle. So, if we consider the instantaneous value of the voltage between base and emitter, starting from the DC value, it will rise above the DC value when the signal is in the positive half cycle and it will fall below the DC value when the signal is in the negative half. So, we have instantaneous voltage between base and emitter represented by this waveform. So, starting from here we can see in the positive half cycle of the signal it will be rising and in the negative half cycle it will be falling. So, instantaneous value of base to emitter voltage will be like this. Correspondingly, base current, if we see the DC base current is this one, when the signal is increasing, the base current will be obviously increasing because of the more biasing in the forward region. So, the voltage is increasing and then when it falls, the input signal falls in the negative half cycle, then the base current will be also decreasing than the DC value. We have this representation of the base current, and for example, we are considering a triangular signal. You can have sinusoidal signal or triangular signal, but it is periodic and in the input. We are considering a triangular signal in the input. So, this is the triangular shape we are showing. Now, this is happening because the input circuit is having this VBB plus this signal VI. So, VBB is the DC value, DC voltage which is forward biasing. So, VBB is this value and it will be increasing, this VBE will be increasing because of this small signal from this VBB value and it will be falling also in the negative. So, this is the VBE value DC and AC, and this is the value of the increment of this biasing voltage and the decrement of the biasing voltage in this circuit. So, you have to notice is that this is the biasing voltage, but base to emitter voltage in these voltages are not same, because the base to emitter voltage is after the drop occurs here we get the base to emitter voltage, that is this voltage minus this drop. The drop occurring across RB is because of this instantaneous current IB. So, this voltage minus this drop equal to VBE. So, here it is this, in this graph both are shown, that is this is the biasing voltage, but this is the voltage between base and emitter and this is the corresponding base current. Now, in the input circuit the DC load line can be drawn by connecting the maximum and minimum values on the x and y axis, and so maximum value for a particular RB, because if we change this value of RB our load line will differ. So, for a constant RB, suppose for a particular RB, if we want to draw the load line, then this maximum point and maximum point of this base to emitter voltage, and if we consider this point which will be maximum on the IB, then it will be happening when you make this VBE 0. So, the load line, DC load line, if we consider DC load line, then without application of the input signal, the load line will be like this. That means, here VBB will be the maximum value of the voltage available across the base to emitter junction. That will happen when IB current is 0, and the maximum value of the IB current will occur when base to emitter voltage is 0. So, that is another point, maximum point. If we join this, we can get the load line, and for a particular value of IB that you are choosing, or for a particular value of RB, the intersecting point between the characteristic and the load line will give you the operating point, that we all know, and the slope of that load line is minus 1 by RB, minus in because it is decreasing. I mean this slope is such that the straight line is having a negative slope, that is why it is negative, and 1 by RB, that is the slope. Now, corresponding plot in the output, that if we look into output characteristics, we see here the output characteristic is nothing but a plot between IC and VCE, and here it is instantaneous current and instantaneous voltage, combination of both DC and AC. So, now corresponding to a particular IB, we have that particular value of IC. So, as IB is increasing from its DC value, correspondingly IC will also increase. So, initially when there is no signal, then the DC value of that IC is the capital I capital C, that is this point. Now, base voltage is increasing, VBE is increasing, base current is increasing, correspondingly there will be collector current increment, because now the AC component, AC current small I small c will be added up with capital I capital C, and small I small c is nothing but beta times of small I small b. So, this collector current will also increase. Similarly, when the base current decreases, collector current will decrease. So, we get this increasing and decreasing collector current across collector to emitter voltage. Now, considering collector to emitter voltage, when there is no signal, means only DC conditions are prevailing, we get this is the operating point, that is the intersecting point between the load line and the characteristic. So, this DC value, which is VCE DC value, is the collector to emitter voltage. Now, the value of VCE when collector current increases is given by VCC minus ICRC. So, VCC minus ICRC is equal to VCE. Instantaneous value if we consider, then this instantaneous value of the voltage between collector and emitter, that is equal to this VCC minus ICRC. Now, if IC goes on increasing, if IC increases, then obviously this whole quantity will be decreasing, because it is negative. ICRC drop will increase means VCE will decrease. So, this is an important fact to be noticed here, is that when collector current increases, collector to emitter voltage will be decreasing. So, it is because of this negative factor here. So, it will be decreasing when IC increasing. So, here starting from this DC value, when IC is at this peak, we will be getting the negative peak of the VCE. So, this point is important. When IC is minimum, then we will be getting this VCE maximum. Now, for a particular value of resistance in the collector, we can draw the load line, this load line, DC load line if we want to draw, joining the maximum points on the voltage as well as the current axis. Maximum point of the voltage is obviously VCC when you have 0 current in the collector, maximum voltage will be available and that cannot exceed VCC. ICRC drop is 0, so VCC is the maximum point, and the collector current will be maximum when you have VC is equal to 0 and that value is VCC by RC. Joining these 2 points, for a particular RC we get a load line. Now, intersecting point between this load line and the characteristic for a particular base current at which it is the transistor is being operated, that is given by this point which is known as Q point, that is the operating point, and this operating point is the point which is the DC point. That means, we are not applying any signal. What will be the collector current and collector to emitter voltage, that is given by the Q point or quiescent point it is called. Quiescent means it is called silent point, meaning is that it is not having any signal in the input. That means, it is not having any AC voltage in the input, only DC biasing voltages are there. So, this Q point will be giving you the operating condition of the transistor, and for a particular resistance in the base, we have a particular value of IB, and for that particular value of IB, this is the Q point. If we go on changing IB for different values of IB, obviously we will be getting different Q point. And the slope of this load line is minus 1 by RC, minus because it is a negative slope, as is clear from this straight line, the slope is negative, and 1 by RC will be giving that slope. So, from this slope we can basically know about the resistance which is connected in the collector. So, here we again are considering that DC as well as AC conditions prevailing together. So, we have, apart from this DC biasing voltage, this signal is there, that is the AC signal which you want to amplify. So, basically why amplification is happening in the transistor, that we will be discussing in details later, but for the time being we have to see one point. When we tell about amplification, we mean amplification of the AC signal. So, while dealing with amplification of a signal, we will be concentrating only on the AC conditions, and DC conditions are only for biasing the transistor properly, and for amplification or the operating the transistor as an amplifier, we will have to deal with the AC conditions prevailing exclusively. But now again, if we consider what is this collector to emitter voltage, this point is collector, this point is emitter, this point is base. So, collector to emitter voltage is equal to VCC minus ICRC. In this output circuit, if we apply the Kirchhoff's voltage law, we get this VCC minus ICRC is equal to VCE, and ICRC we can write this if we now again write that VCC minus ICRC equal to VCE. Basically, what we are writing by this equation is the instantaneous voltage between collector and emitter, that is given by this VCC, that is the DC biasing voltage at the collector, which is reverse biasing, minus ICRC. This ICRC, if we consider this IC, now this IC is basically it is that instantaneous current having IC plus small IC, but only we will be considering AC voltage in order to discuss about amplification of the transistor, and then we will be concentrating only on the AC component, and AC component in this VCC minus ICRC is only that small I small c and RC, that product which will be now used for finding out the amplification. And basically voltage gain happens because this product of this current and this resistance at the collector, if we consider alone, IC is nothing but beta times of IB. So, the voltage gain, if we consider, that is the ratio between the output voltage and the input voltage. You are getting an output voltage V naught at the collector point. That voltage, if we name it V naught as the output voltage, V naught is basically minus small IC into RC, and this minus thing is happening because that we have seen just now, increment of IC will cause decrement of that VCE. So, this minus ICRC, if we consider with respect to this input voltage, then we will be coming later to know that will have a very large amplification factor. V naught by Vi will be very large, hundreds of gain we can have, because of the fact that in common emitter transistor, when it is used as an amplifier, that IC is nothing but beta times of IB, and input voltage will be this base current into the resistance of the transistor, input resistance of the transistor, and input resistance of the transistor is very small. So, finally, what we will be getting is V naught by Vi in terms of beta, and that beta is very high, and this beta will be affecting the overall gain. So, why a transistor in common emitter configuration is used, because IC is equal to beta times of IB. So, this beta value is high, and again it will be multiplied by RC. So, the whole thing, this product will be high with respect to or in comparison with input voltage. So, basically we get an amplification occurring in the transistor amplifier, and how this amplification occurs we will be discussing in details. But at this point, what is to be noted is that the signal should not be distorted while being amplified. Meaning is that, suppose we are trying to amplify a small signal, which is a signal is, say for example, sinusoidal signal we are amplifying, then the output which we will be getting at this collector point, that is V naught with respect to ground. If we find out V naught and see in the oscilloscope, basically I must get a voltage which will be just similar in shape, exactly in the same shape as the input voltage, but it is to be magnified. That means, I expect a waveform V naught which will be like this in nature, that is the magnitude is amplified many times, but the shape is exactly same. If it is sinusoidal input, I must get a sinusoidal output at the collector end. If it is a triangular, I must exactly get a triangular. Of course, this will be not exactly in this same phase, we will be finding later, it will be have an opposite phase. That means, output voltage in common emitter transistor will be basically out of phase with the input. Basically, this will be the signal. How this signal is coming out of phase? One hint we have got just now, that it is negative with respect to the collector current, and collector current is again in phase with the base current. So, basically what will happen is that the output voltage will be out of phase with the input voltage, but nowhere during this amplification the shapes should change. That is, we should not get an output voltage where a portion may be clipped in the positive as well as or in the negative region. That means, I should not get an amplified signal which is like this or like this. And to ensure that, one point is important, that we must properly bias the transistor. So, the transistor must be biased properly, that means we have to now again look into the DC conditions prevailing. So, I again consider the DC circuit which biases the transistor in the active region. So, the input circuit, if I consider, draw the load line, then this is the input circuit DC biasing point. The biasing point means this will give you, this point will give you the value of the DC voltage and the DC current in the input circuit, which is the base emitter circuit. So, in this circuit, what is the value between base to emitter and what is this base current? That is known by this point which intersects the input characteristic and the input circuit load line, and that is evident from this input circuit equation. If we write down the Kirchhoff's voltage law equation in the input circuit, VBB minus IBRB equal to VBE. So, I can draw this load line very easily. If I make VBE is equal to 0, then IB is equal to VBB by RB, that is this maximum point, and when IB is equal to 0, this VBE is maximum, which is nothing but it becomes equal to VBB, the base biasing voltage. Joining these two line, I get 2 points, I get this load line. The point where it intersects this characteristic, input characteristic, that gives the input circuit operating point. Now, similarly in the output circuit, if I want to draw the load line, find out the operating point, I must join these two maximum points. That is very easily obtained from the output circuit. If I apply Kirchhoff's voltage law in this circuit, in this loop, VCC minus 2 plus rising minus ICRC minus VCE is equal to 0. So, VCE is equal to VCC minus ICRC. Here when I put IC is equal to 0, I get VCE is equal to VCC, that is the maximum voltage that is available on the x axis, that is the voltage axis, and when VCE is equal to 0, I get the maximum collector current that is possible, which is equal to VCC by RC, that is this maximum collector point. Joining these 2 points, I get this load line, and for a particular IB which was this IB, for that particular DC condition of the input circuit, means for a particular IB which is determined nothing but then only this resistance in the base circuit. So, for that particular IB, this is the operating point, because this particular characteristic, output characteristic for a particular IB we are considering, intersects this DC load line at this point, which is Q. This Q is the operating point or quiescent point or silent point, it is named, various names are there, but this point is nothing but the point which determines the DC condition in the output circuit. So, the operating point is one important point we must first set, that is setting the operating point properly is the basic criterion for proper amplification in a transistor amplifier. So, what is this importance of properly setting the operating point, or by what factor we will be telling or ascertaining that the operating point is proper? If we look into this output characteristic and this load line, here it is the operating point, it is almost in the middle of the load line, that is the operating point is situated almost at the middle of the load line. This is an important fact, because if the operating point is not around the middle of the load line, or if the operating point is much closer to the cutoff region or to the saturation region, then we will be not getting a distortionless amplification of the input signal, which can be verified by examples. So, what is the effect of this Q point location on the allowable signal swing? That means, I want to get as much larger swing as possible in the output. suppose I am giving an input signal, a very small weak signal, I expect that my output signal at the collector should be having a very huge swing, means I must get peak to peak values, this swing must be as wide as possible. That is also considering that the swing must be distortionless. I should not get a clipped off output voltage, clipped out output voltage. So, if we look into the output circuit again, then here the Q point is determined by this fact that for a particular IB, this intersecting point between the load line and the output characteristic in the DC circuit, that is the Q point. Now, if I have a different IB, my Q point will be here. Suppose I am considering for this IB, IB can be different only when I change this RB value. RB value is determining the IB. So, if I have different RB, I may have a IB here, I may have a DC value of IB here. That means the Q point will be shifting above or below the ideal point. Now, if I have such type of condition happening that my Q point is suppose shifting to this or this point, that means ideally I am not having in the middle of the load line, I mean my load line is now different for different values of say output resistance, output circuit resistance. If I change RC value also, if I change, then the load line slope will be different. If I have a different RC value in the output, then the slope of the load line in the output circuit will be different, as is evident here. This load line and this load line, load line A and load line B are different, the slopes are different because of the fact that the slope is determined by the resistance in the collector RC. So, if I change RC value, I have a change in the slope of the load line. Now, changing the slope of the load line will be having an effect on the Q point. Now, the Q point if I see, then for a particular IB I am considering, same IB I am considering, suppose I am not changing RB value, input resistance value I am not changing, base resistance RB is same. Then because of the slope being different, it is intersecting the IB characteristic here, and if the slope is different by this load line B, it is intersecting at another point QP. Now, when I have different Q points as different from the earlier cases, now it is this Q point, suppose load line A having this Q point QA, and for that Q point QA I am having the voltage at the collector to emitter by VCE. So, the voltage at the collector, if I consider the QA load line, then as we see that this operating point is having this DC value, okay, this DC value is very close to the cutoff region. Cutoff is when you have this IB 0 below the IB 0 portion will be the cutoff region. So, if it is suppose starting from this point, then what will happen is that when you increase this base current, this base current is increasing, collector current will increase. So, collector to emitter voltage will increase, and when you decrease this base current, collector current will decrease and collector to emitter voltage will increase. So, if I see the VCE profile, now in the positive swing, if I look into the positive swing, I see that the instantaneous value of the collector to emitter voltage is clipped in this portion, because at any point the value of the VCE cannot be greater than VCC. VCC is the supply voltage we are providing. If we look back into the circuit, this is the supply voltage which is reverse biasing, which is VCC. So, at any point you cannot have a value VCE greater than VCC. So, our upper point, this point is fixed, we cannot go beyond this. So, if the operating point is closer to the cutoff region, then we see that our one portion of the positive swing is cut off. We will be getting an output which will be clipping off one portion in the positive cycle. Similar positive half cycle. Similarly, if we consider this load line, this is the operating point. What will happen is that in the negative half cycle, we will be as this point, the operating point is closer to the saturation region. What will happen is that in the negative half cycle, this is the maximum collector current that can flow in the circuit. Its upper point is fixed by the load line, which is VCC by RC. You cannot go beyond this point. So, if we increase this, if we consider the negative swing from this DC value, it will be negatively, it will be increasing, but it cannot increase beyond this point. So, this region will be cut off, but of course, upper portion does not have any problem. It will be having the undistorted swing in the upper portion or positive portion, but the negative portion has a clipped off representation, and that is not desired. We cannot get an amplification which is distortion, having distortion, that is not desired. So, what we infer from this is that if the operating point selection is not proper, either it is too close to the cutoff region or too close to the saturation region, then what we will be getting at the output, that signal will be not distortion less. That means, it will be either clipped up in the positive or clipped up in the negative portion of the cycle, and that is not desired at all. So, this Q point selection must be proper, so that maximum undistorted swing in the output signal is obtained. So, first and foremost thing that we have to emphasize is proper biasing of the BJT, that is DC biasing of the BJT is to be discussed first, and once we ascertain that it is properly biased, then only we can proceed to have distortionless amplification of an weak signal. So, again I just want to show the output signal having negative peak clipped off, just as we discussed just now. When you have the operating point very close to the saturation region, your negative portion will be negative, signal will be not distortionless, it will be having a clipped off region. Ultimately output will be like this, and if we have the operating point very near to the cutoff, then we get a clipped off version in the positive swing. So, output signal will be like this, there will be a clipping off of the positive part of the signal, and we do not want that. So, we will be now concentrating how to bias the BJT properly. Biasing means application of these C voltages to establish a fixed level of current and voltage. That means, it is proper selection of the Q point to suitably accommodate maximum undistorted output signal swing. That is the aim of our DC biasing. We have to select the Q point properly such that we have maximum undistorted swing in the output signal. Maximum undistorted swing means in the output signal there should not be any clipping of any portion in the output signal. But again, once we select a Q point properly, it must also not be shifted. That means, once we select a Q point properly, suppose we have selected the Q point at the middle of the load line just to have the maximum undistorted swing, suppose like this, but once even after selecting the Q point properly, it may so happen, and it happens that Q point shifts either towards above or towards below the properly selected initial selection. Then again we will be facing with the same problem. So, once we select Q, we must also guarantee that it is not being shifted because of change of beta value or change of temperature, because when this Q point will shift, if for any reason even after selection of the Q point the collector current IC, suppose it is changed, then if it is becoming higher, then it will be shifting to the top, and that happens because of two reasons. One is change of beta value. If suppose during operation of the amplification or operating the transistor as an amplifier, while doing so we are suppose changing the transistor, because of various reasons it may so happen that you have to change the transistor. And if we change the transistor, this beta value will not be same, because it is very difficult to have the same beta value for two different transistors, although even if this fabrication is very much advanced nowadays, still exactly having two beta values same is difficult. So, your transistor when it is changed, it may have a different beta value. If beta value changes, then definitely IC will change. IC is equal to beta times of IB. Even if you are keeping IB same, you are not changing IB, but still IC is getting changed because of change of beta value. Another factor is also there which affects that change of IC is temperature. As if the temperature has a variation, if the temperature suppose rises while doing the operation of amplification, suppose the transistor is increasing, and we know that transistor this temperature is suppose increasing, and if temperature increasing, we know that reverse saturation current, leakage current increases, and reverse saturation current will increase if the temperature increases. That we have seen earlier while discussing diode also. So, for every 10 degree centigrade rise in temperature, we have seen that the reverse saturation current almost doubles. So, that is why reverse saturation current increases with rise in temperature, means ultimately IC will also increase, because IC is equal to beta times of IB plus beta plus 1 into IC naught. So, if IC naught rises because of the rise in temperature, ultimately IC will increase. So, IC will increase means again the Q point will be shifted. So, you may reach again near the saturation, or vice versa. If IC if temperature is decreased, you will be having a decrease in IC because of fall of IC naught, and Q point will shift towards cutoff region. And this should never happen once you select that Q point, that has to be ensured. So, we will be discussing about how different biasing schemes operate. We will be first of all discussing the different biasing schemes, and then see which biasing scheme is best or better with respect to this shifting of Q point, that means stabilization of Q point. Stabilization of Q point we will be discussing afterwards. Before that, we will be starting to discuss the different biasing schemes, and the simplest biasing scheme is fixed bias, that is a very simple circuit having only a resistance in the base region and the collector in the collector region. This circuit is just the circuit of the amplifier, and mind it, here we are applying AC signal and we will be getting the output AC signal at the collector. These capacitances are there which are known as coupling capacitors to couple the AC signal to the transistor. What is the role played by this coupling capacitors we will be seeing later, but before that we will concentrate on the DC equivalent circuit for this amplifier. So, the fixed bias circuit is this one, which is used as a transistor amplifier having NPN transistor. As usual, we are discussing NPN transistor in the common emitter. If we consider only the DC circuit for this transistor amplifier, then capacitors will be now ignored, because these capacitors are open circuit for DC. If we consider the reactance of the capacitor, 1 by 2 pi f c is the reactance, 2 pi f into c. Now, frequency for this DC circuit is 0. So, if f is 0, then this whole capacitive reactance offered by this capacitance is infinite. So, when this capacitance is offering infinite reactance, there cannot be any current flow, that means it is equivalent to open circuiting this and this part. So, under DC condition, that means we will have a circuit bereft of these capacitors, without these capacitors, because capacitor is open circuit like DC. So, the DC equivalent for this fixed bias circuit is this one, and here in this DC circuit, this is purely DC circuit. So, we have to now find out the DC point, operating point or Q point. DC operating point we have to find out, means we have to find out IC and VCE for this particular IB, because IB is set by this resistance RB. So, now if we just simplify, we just redraw the circuit conventionally just for easy understanding. I am just separating the VCC source. If you look into this circuit, same VCC is there for this base circuit as well as collector circuit. It is sharing, both the circuits are sharing the same VCC. I can redraw it more conveniently by separating out these two VCC sources. This is same circuit, only for easy understanding I have just separated them out. So, now my analysis will become easier, because if we now concentrate on the input circuit, that is the base emitter circuit, if apply Kirchhoff's voltage law in the base emitter loop. So, application of Kirchhoff's voltage law is VCC minus IB into RB minus VBE equal to 0, or I can write down what is IB. IB is equal to VCC minus VBE by RB. This is the base current in this DC circuit, which is set by RB. Others are constant, you mind it, here VCC is constant, because we are applying a particular reverse biasing voltage as well as a particular resistance and RC, and RB, for that particular RB, IB is set, because VBE is 0.7 volt for silicon, it is constant. So, this is the base current. Corresponding to this base current, the collector current, DC collector current which is flowing is beta times IB. So, I can write this expression again, it is beta into VCC minus VBE by RB. So, this is your DC value of collector current, and again using this Kirchhoff's voltage law in the output circuit, that is in the collector to emitter loop. If I consider this loop starting from this point ending again here, apply Kirchhoff's voltage law, algebraic summation of all the voltage drop is 0 in a loop, and applying that I get VCC minus IC RC minus VCE is equal to 0. I must start from the same point, I must end up in the same point, that is a loop. So, VCC minus ICRC minus VCE is equal to 0. So, from here I get what is VCE, VCC minus ICRC. This IC I have already calculated, from this expression I know what is value of IC. So, now I know what is the value of VC, I know what is the value of IC. So, I have now fixed my operating point Q. This is a simple biasing circuit known as fixed bias, but we will be seeing later on that as per the stability of this operating point is concerned, it is not a very good circuit, because it is very sensitive to beta variation as well as temperature variations, and that is very evident here. If I have a change of beta, obviously it will be affecting this collector current, because in this expression itself you can see that beta is coming into that expression. So, beta change means the collector current will change. Similarly, if I have a change in the temperature, suppose temperature is increasing while operating the transistor, then collector current will increase because of the increment of the leakage current IC naught. So, again that IC will increase. So, IC will increase means your VCE will also be affected by that IC. So, whatever Q point I have shifted, now it will be I have set, now it will be shifted again. So, once I set this Q point, it is not guaranteed that it will be remaining in the same position. It will be shifted because of the fact that it is very sensitive, this circuit is very sensitive to beta as well as temperature. That means it is not a good circuit. Now, another circuit is there for biasing the transistor is emitter feedback bias. Here there is a feedback resist, the emitter is having a resistance. This why it is called feedback we will be discussing again later, but for the time being this is the circuit which is emitter feedback bias. That means The difference between the earlier circuit fixed bias and this circuit is that there is an emitter resistance, that is the difference, other part is same. So, in this circuit also, if we consider the DC equivalent circuit only, that means DC conditions when prevail, there will be open circuiting by this capacitors C1 and C2 in these two points, there will be open circuit. So, we will be left with this DC circuit without these capacitors, and again I am separating out these two sources VCC just for easy understanding, nothing else than that, and then I can analyze the circuit separately. If I consider the base emitter loop, apply the Kirchhoff's voltage law in the base emitter loop, mind it that through this emitter resistance the current which is flowing is IE, emitter current. So, what will be this loop equation? VCC minus IBRB minus VBE minus IER equal to 0. You do not forget about this base to emitter drop. You cannot neglect or ignore that base to emitter drop, which is constant 0.7 volt for silicon. Now, simplifying this circuit a little, this expression a little, I can represent IE by IC plus IB. So, representing this IE by IC plus IB, I now can take IB common, because IC again can be written as beta times IB. So, what will be finally obtained is that this expression VCC minus IBRB plus beta plus 1 into RE whole bracket minus VBE is equal to 0. So, what is the expression for IB? IB I now get VCC minus VBE by RB plus beta plus 1 into RE. Again IC is equal to beta times IB. So, IC can be known if I know beta IB, and I can also know IE, which is equal to IC plus beta. So, from this, starting from this expression, I know IB first, then I can calculate IC. When I know beta, I can calculate IC, and then I can calculate IE by simple expression, because IE is nothing but IC plus IB, or even I can write it as beta terms of IB plus IB. So, beta plus 1 IB is equal to IE. This or this expression is same. In the collector emitter loop, if I consider, again apply the Kirchhoff's voltage law, VCC minus ICRC minus VCE minus IER equal to 0. So, from this expression I get what is VCE? VCE equal to VCC minus ICRC minus IERE. One more step further I can do by some approximation, which is a very valid approximation, because IE is almost equal to IC, IB is in the order of micron. So, I can write this expression approximately as, this is actually approximate equal to VCE is equal to VCC minus IC plus IE into RE, because I am now, if I now consider IE is equal to IC, then I can combine these two. So, that will be, this will be, no, this is not wrong, right, VCC equal to VCE equal to VCC minus IC RC minus IC RE, then I can write, which is equal to VCC minus IC into RC plus RE. So, this is not right, this is the expression VCC minus IC into RC plus RE. That means, I am taking this IE to be equal to IC. With this approximation, I get a simpler expression than this, but exact equation is this one, only simplification a step further will be giving you this equation. Also here, if I want to find out what is this voltage at this emitter point with respect to ground, that I can find out VE, suppose that voltage is equal to IE into RE. And what is the voltage VC? When I mean VC, I name VC that represents with respect to ground. So, there is a difference between VC and VCE, mind it, VC is between the terminals C and E, but when I say VC, it is equal to, it is the voltage at collector with respect to ground, and that is equal to VCC minus ICRC. And what is the voltage at B? That is VB, VB equal to VCC minus IBRB. Or again I can write another expression for VE, which is equal to VB minus VBE is equal to VE. So, this also I can write. So, all these voltages and currents I can find out in this circuit. So, this is a emitter feedback bias circuit. So, two circuits we have discussed. One is the fixed bias circuit and the second circuit is emitter feedback bias circuit, where there is a resistance in the emitter, that is RE. So, if there is a resistance in the emitter, then our whole expressions for current and voltage have become little different from the fixed bias. Fixed bias is the simplest circuit, but that is not good for stabilization of the operating point. One improvement has been done by incorporating the resistance in the emitter. How it is going to stabilize the operating point, that we will be observing later. So, we have still more circuits for biasing a transistor, and these circuits will be further and further improvements over the basic and very naive fixed bias circuit, and those we will be studying gradually one after the other and see the drawbacks as well as advantages of each biasing circuit.